Okay, so we are going to talk about momentum and collisions. It is raining, so you'll hear a little rain in the background. We're going to start with the concept questions. Remember, we talked about three types of collisions. There is perfectly inelastic, which is when two things stick together after they collide. There is elastic, which means they bounce off of each other and they have the same amount of kinetic energy after the collision as they had before, which means kinetic energy was conserved. And then in between the two extremes, you have inelastic, which is if they bounce, but they lose some energy in the process. So first of all, we have the type of collision when they collide and stick together. That one is perfectly inelastic. Okay. The kind where they collide and bounce off, but they lose some kinetic energy is inelastic. There's varying degrees of inelasticity, but they are all inelastic. And then this one, they bounce off and have the same amount of kinetic energy after as before. That's elastic. So now these are descriptions of some specific collisions. So one, you have two billiard balls collide. They started off with 3.4 joules of energy at the beginning, and after they had the same. That means it has to be elastic because they had the same energy before and after the collision. Number 5, collides. They start with a total of 35 joules of energy, and then afterwards they end up with 30 joules, which means we lost some energy, which means this is inelastic because the bowling ball is not connected to the bowling pins. So it's not perfectly inelastic, but they did lose some energy. And then the last one, they collide and they hook together. So hooking together is essentially like one form of sticking together. And so that is a perfectly inelastic collision. Okay, so now we have some calculations. Okay, so we're going to perform the calculation and we're going to check our rounding and units at the end. So this one, we're trying to find momentum. Remember, momentum is P or rho. You have 1,450 kilograms. That is a mass. And then it's going 15 meters per second. That one is a velocity. Everything's in the right units. I don't have to do any unit conversions. So I have my P equals mv equation. All I have to do is plug those numbers in. And I get 21,750. And then for sig fig purposes, I have 3 sig figs. So I want to keep 3 here, and then I'm going to round. So that's going to round to 21800. And then momentum is in kilogram meters per second or Newton seconds, whichever you prefer. They're equally correct. So then 8, how fast? So I'm looking for a velocity this time. I have a 0.125 kilogram baseball. I have a momentum of 3 kilogram meters per second. And so same equation, P equals mv. I'm just solving for v this time. So I'm going to divide the m over. I get 3 over 0.125, and that's going to equal 24 exactly. And it's a velocity, so it's meters per second. Okay, so that's that one. Let's go to the second page. Sorry, I realized the camera's a little shaky today for some reason. Okay, so start with number 9. So these are some problems about impulse. So how much force is required to stop a 0.42 kilogram football traveling that speed in that time? So there's a lot of pieces here. So how much force, that's what I'm looking for, is force. I have a mass of 0.425 kilograms. I'm trying to stop it, so my final velocity is going to be 0. It's currently traveling 16 meters per second. and then my time is 0.15 seconds. Okay, so looking at that, I can see I have my impulse equation. So I have F delta T equals M delta V, which is also just M times V minus V naught. Looking for force, so I can just divide my time over. So my force is going to be mass, which is 0.425, times V, which is 0. So this is negative 16 over 0.15. And if I multiply all that together, keep in mind that negative is important. So I have 44.8 is my answer. The negative there just means that you have to push in the opposite direction of where you're going initially, which makes sense. If you're going to stop something, you need to push against where it's going. So that's the directional piece. So I'm going to round that to negative 45, and this is a force, so it's going to be in newtons. Okay. This one actually asks for the impulse, which is the entire F delta T or M delta V. So impulse can be either piece of that equation. You just pick the one that matches the numbers that you have. So I have a mass and 2 velocities, so I'm going to be using this portion of it. So it's going to be, I have a 68 kilogram person is my mass. I'm going from 4 to 1.8. So my initial velocity is 4, final velocity is 1.8. Everything's in the right units. So I'm going to do M, which is 68, times final minus initial. So 1.8 minus 4. So I end up with negative 149.6, which is going to round to 2 sig figs, which is negative 150. And then impulse is the same as a change in momentum, so they have the same units. So again, you can do Newton seconds or kilogram meters per second. Those are both equivalent. It's whichever one you like better. Okay, and then the last one with impulse. Again, impulse can be either F delta T or M delta V. This time I have a force and a time, so I'm going to be using this portion of the equation. So my force is 150. My time is 0.050 seconds. I'm looking for impulse. So impulse equals 150 times 0.05, which is going to be 7.5 Newton seconds. I typically put the Newton seconds if my problem involved newtons and seconds. And I typically put kilogram meters per second if it did not. But again, totally up to you. Doesn't matter which one you pick, they are the same thing. Okay, so let's do 2 different collision problems. I do have extra problems. If you need them, I'm going to post the problems and answer key if you want more practice with these. So you have an 84 kilogram football player, so that's my first mass. Remember, with these ones, you want to be most careful that you write down the information carefully in a way that you don't get things mixed up. So he's tackling a 72 kilogram football player, and he's stationary, so his initial velocity, let's call it V2, sorry, V2 is 0. After the collision, they're traveling 1.5 meters per second together. Okay, I'm going to use V final for that. I don't have a 1 or a 2 on it because it's the same for both of them. How fast was the running player traveling? So that's V1. That's what I'm looking for. And then how much energy was lost and what type of collision is this? So first I want you to do the momentum piece. So there's 2 ways you can write this. You can do 2 separate objects before and then 1 big object after. or you can do the same thing on this side and still do the same 2 terms after. Okay, notice it's the same V. Now if you look, this is just this, but the V got factored out. So again, it doesn't matter which of these you start with, they are the same. So these are equal, so you just pick which one you like better. From there, we're going to get to the same answer. So you're going to start with this being 0. So I have an 84 kilogram guy going some speed that we don't know equals 84 plus 72 times 1.5. So my V1, I'm just going to divide that by 84. So I multiply and add and all the things, I get that to be 2.7857, which I would round to 2.8 meters per second as my answer. Okay. Now, how much energy is lost? You just need to do kinetic energy before and after. They're going to pair up the same way they paired up here. So before, it's going to be, I have one object moving and one that's not, so I'm just going to do 1 mv squared. And when I do that, I'm going to use a non-rounded version of that, so 1/2 times 84 times 2.7857 squared. I end up getting 325.925. That's the energy I had, or the guy that was running had previously. And then after, you have 2 people acting like one big mass. So m1 plus m2, 1/2 mv squared. So I get 1/2 times 84 plus 72 times 1.5 squared. And that one gave me 175.5. So to see how much was lost, you just subtract. So do 325.9 minus 175.5. You get approximately 150 joules of energy lost. That's what was lost in the collision. Now, based on that, we need to look at that and the fact that they kind of were moving together as one mass, and I get a perfectly inelastic collision because they're acting like one thing after. Okay. So then on the second one, this is a not sticking together problem. So this one, it tells us it tells us that it's an elastic collision. So I have 2 different objects. So I have an M1 and an M2. So I have a mass of 5 kilograms for one of them. It's rolling to the right. Okay, so I'm going to pick right as positive because it's just typically what we do. So the velocity of the first one before the collision was positive 3.5 meters per second. The second ball has a mass of 3 kilograms. It's rolling to the left, which is negative 7.5 meters per second. After they collide, the 5 kilogram ball, which is this one, is rolling to the left at 4.75 meters per second. And then I'm looking for how fast the other ball is rolling and in which direction. I don't know if it's turned around or not, so we're gonna have to get the answer. If we get a positive number for our velocity, that means it's going to the right, and if we get a negative, it's going to the left. So we're trying to find this. So let's start. We definitely have 2 objects before and 2 objects after this time. Remember, I'm just using the little tick mark to indicate the after. You can kind of do whatever subscript, superscript deal you want, as long as you can tell the 2 apart. So in this one, nothing's 0, unfortunately. So I have 5 times 3.5 plus 3 times negative 7.5 equals 5 times negative 4.75 plus 3 times b2 prime. So I do this whole side comes to negative 5. This term comes to negative 23.75. No, it's not squared, just a prime. So I need to add this over. So remember, these are just being added, so I don't want to divide anything, I just add. So this turns into 18.75. And then I divide by 3, and I get, I don't know, I keep squaring that. There we go. I get 6.25 meters per second. So that would be 6.3 meters per second, and it's a positive number, so it's going to be going to the right. Okay, now it says how much energy was lost in the collision. Well, it told us it was elastic, so the answer is 0. If you want to check it, you can. You just do 1/2 mv squared for each ball before the collision, each ball after the collision. It does come out, I checked it. It comes out to, let's see, do it again. 93.125 joules before and after. Nope, it does not, because I did not square my second velocity. It comes out to 115 before and after. So you can check that if you would like. If it is elastic, though, we know that it didn't lose any energy. So that's about it. So that's all that's on this test.